Welcome, I'm Robin Schmid and I'm a master student at the Robotic Systems Lab at ETH Zurich. I'm happy to present you our work on self-supervised traversability prediction. This work has been conducted in joint collaboration with the NASA Jet Propulsion Laboratory for fast autonomous off-road vehicles. Most recent advancements in robotics and autonomous driving have created big interest in deploying these systems in unstructured wild environments. Navigating in the wild requires a perception system that can differentiate traversable from non-traversable terrain by incorporating geometric as well as semantic information. In our case, we want to navigate with an off-road vehicle autonomously in the wild and are interested in detecting traversable and untraversable terrain using the experience collected from previous runs. Recent works on learning from past robot experience generate training labels in a self-supervised way. In a work from Lawrence Wellhauser et al., the robot's trajectory gets projected into the camera image and labeled with the proprioceptive information. This allows to learn a model to predict this proprioceptive information on new terrain. Since this only learns on positive samples, the model is bad at predicting for out-of-distribution samples and also does not treat the case of occluded trajectories. However, a way to deal with learning from just positive samples are anomaly detection algorithms. In recent works, this has been used to recognize regions the model has never seen during training or marks them via the reconstruction error as novelties. We want to include this principle in detecting traversable and untraversable regions. Since we're operating on unstructured terrain, we also need to handle occluded trajectory parts. This brings me to our method. We see our contributions in three parts. First, we develop a tool to project the recorded wheel trajectories into the front camera image. Second, we then apply an occlusion filter which removes occluded trajectory parts. For each wheel contact point, we do a nearest neighbor search, which finds the points closest to the camera to the wheel point ray, compare the distance to the camera, and then remove these occluded parts. This gets a mask with visible traversed ground, like here in green. Lastly, we train an autoencoder on masked image regions. During training, we just train on masked image regions and assign no loss to the parts outside the mask. For inference, we use the reconstruction error as a measure to distinguish high and low risk traversability. Like here, black, the ground is low risk, and white, the vegetation or stones are high risk. For our model, we use a variational autoencoder with a MSE loss, which we multiply with a binary traversability mask. We use the reconstruction error as a measure to assess risk for traversability. In our experiments, we compare the performance when using different bottleneck sizes and model backbones, such as a ResNet 18 or 50. We evaluate our approach by collecting around 30 kilometers of driving data from 2 test sites in California. One from the Arroyo, just next to the Jet Propulsion Lab, with grounds and logs as terrain, and one from Mojave Desert with sand and small vegetation. We trained models on both test sites and tested them on both of them for generalizability. Driving off-road, we have had a number of occluded trajectory parts in the projected trajectories, mostly from vegetation. Since occlusions were at a close distance and some at the further, our tool was still able to project the future wheel trajectories and remove occluded parts for both of these distances reliably. With this, we had zero human labeling effort to create our training data. Here an overview of some predictions of our model. If you have a look at the last row with the reconstruction error, we see a clear difference in the reconstruction of ground versus vegetation. The ground is clearly predicted as low risk and the vegetation and rocks or sky as high risk. We were curious to see how this compares and evaluates to ground truth data. We compare each model to independent test sets from Mojave and Arroyo with different bottleneck sizes and backbones. The ROC curves show that the Mojave terrain model generalizes well, demonstrated by its similar performance on the 2 test sites. However, the Arroyo model shows a lower performance on the Mojave test set. While these semantic labels are not a direct match to traversability risks, since they do not capture the vehicle's capabilities, they are a good approximation, as vegetation ideally would have a higher risk regardless, due to the potential unknown hazards or tire puncture risk. Interestingly, the Arroyo has more untraversable vegetation, and the model also predicts a higher percentage of this vegetation as high risk compared to the Mojave data. Our best models achieve to predict between 80 to 85% of ground as low risk and vegetation as high risk. One of the primary sources of errors within the predictions are shadowed regions on the ground that are predicted overconfidently. Interestingly, we observed that better results were obtained with bigger bottleneck size, and using a deeper model didn't really impact the results. To conclude, we showcased a new approach to detecting traversable terrain by learning from only past robot experience. Our model was able to separate high and low risk terrains with zero human labeling effort and achieved around 85% of correctly classified classes. Our future works include predicting sparse terrain information, such as speed, vibration, or wheel slip. Further, we want to add negative training data that can also help the model with ambiguous cases. Thank you for your attention. If you have any questions about our paper, I'm very happy to answer them now.